Hi everyone, thank you very much for having me here today. So as Rachel mentioned, I'll be talking a lot about asteroseismology today, and more specifically asteroseismology for massive stars, or anything that has a convective core on the main sequence and up. All right, first of all, what I really hope you take away from this talk today is asteroseismology is really an amazing tool for trying to study stars and learn more about the interiors of these stars themselves. Again, the stars that I'm interested in particular, are the massive stars. So more specifically, again, the stars that have convective cores on the main sequence, but also these stars are important for several reasons, and one of them being that one of the nicknames is the chemical factories of the universe. So throughout their lives and death, they're responsible for the production of a lot of heavy elements that we find in the universe, in galaxies. Now, if you look at the general internal structure of these stars, they share similar structure. And here on the left for you guys, you see an inner 3D model of a star that has a convective core and a radiative envelope. So this kind of structure we divide into different regions. We have convective core, radiative envelope, and then we have a transition region between the two. Throughout the main sequence evolution, the dominant source of energy production comes from the C&O cycle, where isotopes of carbon, nitrogen, and oxygen act as catalysts in this nuclear burning. Out of all these reactions in this cycle, the one that is the slowest is where you transform nitrogen into oxygen, so nitrogen-14 into oxygen. And that means that over time, we end up building up an excess amount of nitrogen in the cores of these stars. And if you have any efficient mixing that is happening inside the star, then you can transport nitrogen from the core to the surface and thereby impact the surface abundances of the stars in this way. But also similarly, you can bring in new hydrogen fuel to the cores. And because we have convective cores, that means the mixing is very, very efficient. So any hydrogen that enters this region, you can use as fuel during the nuclear burning on the main sequence. Now, if you look at what kind of mixing might look like inside these stars, I'm showing you here on the right a mixing diagram where you see the efficiency of the mixing on logarithmic scale on the y-axis as a function of where inside the star that we are. And similar to the structure before, I divided this mixing profile into 3 different regions, where you have in gray mixing from the convective core, which is really high. You have green mixing in the envelope, and in between the two you have mixing that referred to as convective boundary mixing that is happening in this transition region. And so one of the uncertainties that we have is that these mixing profiles are not that well constrained, and that leads to major uncertainties in the evolution of these stars and what happens to them as they evolve further on. So to give some numbers and some examples, if we just look at the convective boundary mixing inside these stars and say we have this region right here, and we increase the size of this region, then the 2 following plots shows what happens to the evolutionary tracts of the stars, as well as the size of the convective cores. So you have HI diagram with evolutionary tracts in the middle, where we go from lighter to darker colors, corresponds to going from a small convective boundary mixing region to a wide one. And on the right, you see the inner hydrogen mass fraction profile of the inner 30% of the star, where the bottom part is because of the high mixing in the convective core, and you see the gradient as it turns to the initial hydrogen it had at the start of the main sequence evolution. And what you see is, on one hand, the star's main sequence get extended, they become brighter if you have more convective boundary mixing, but we're also increasing the size of the convective core. And to put some numbers, if we're looking at minimum to a high amount of convective boundary mixing, the numbers that we're looking at for ages is about a 40% increase in age, the amount of time it spends on the main sequence, just from having this convective boundary mixing. And the helium core you end up with at the end of main sequence evolution effectively doubles in size when we have this convective boundary mixing. So that's really important for the evolution of these stars, that we try to get some constraints on the internal mixing of the stars. The way that I try to do this is using asteroseismology. And before I dive into the details, I wanted to go a bit through some history of asteroseismology as well, for those who may not be as familiar with the field. And to give just a brief introduction of how things kind of got started, in a sense. And so one of the first variable stars, pulsating stars that were discovered, are the Mira variables. They were discovered back in 1596 by Fabricius, who was from the Netherlands. And at the time, they thought this type of variable was actually a novae, because the period of the variability is more than 100 days. And then eventually they realized, oh, actually, it's becoming brighter again after dimming. Years later, the Cepheid variables were discovered, and these have been very useful for a variety of fields in astronomy. And more specifically, Henrietta Swan-Leavitt used it to come up with her distance scale using Cepheid variables. So essentially what she did was working under the assumption that all stars in the Small Magellanic Cloud were probably at the same distance to us. And then she looked at how the period of these variables, these Cepheid variables, is related to their absolute magnitude. Now we have the fun bits that there we go, okay. So what she looked at was these kind of relationships that is now also referred to by some as Leavitt's law, where you see as the longer the period of the pulsations, the higher the absolute magnitude, the brighter the stars are, is what I mean, yeah? And so it was realized that we can use this kind of distance scales to measure distances to objects that are very, very far away. And this was actually used later by Edwin Hubble to show that the Andromeda Nebula was not just a nebula inside the Milky Way, but actually a galaxy within its own right, and much further away than the Milky Way than was initially thought. So at the time, the great debate was happening, where they were trying to figure out, is the Milky Way how big the universe is, or is this things that are much, much further away than this? As you'll see here, right up here in the right-hand corner, there's an object that is marked initially by an N as a novae, but once again, Hubble realized that this was actually a variable star, and this is a Cepheid variable. And so he used Leavitt's law to demonstrate that actually Andromeda is much, much further away and could not be a part of the Milky Way. Just to show you what this kind of looks like today, so you see here an image from the Hubble telescope, where you see here the star in question, the Cepheid variable, and how it's changing in brightness, but also in color over time. All right? So in another sense, what Cepheids have been used to figure out is also what the source of energy production is for stars like the sun. And so initially, very, very far back in the days, in the 1800s, one theory was suggested that maybe the energy production that is causing the luminosity of the suns comes from an infall of meteors. I think we all know today that is definitely not the case. Yeah, the energy production you get from that is not high enough, and that would be something we would see if we have that constant infall of meteors. The next theory is maybe the energy production is coming solely from contraction of these stars. And so what Eddington did in this case is to carry out a thought experiment using delta Cepheid as a case study, saying, okay, to be able to sustain the brightness of a delta Cepheid variable, its density would have to decrease by at least 1% over a 40-year period. All right? So that's to explain the luminosity caused by contraction. What was known was the pulsation period is a function of the density of the star. So this would correspond to the pulsation period having to decrease by about 40 seconds per year. However, as you might remember from a few slides ago, this star has been studied since 1785, and what was known is that the pulsation period changes by less than a tenth of a second over years. per year. So this was used to demonstrate that the contraction theory is probably not the one that is explaining the energy production inside stars. And instead, Eddington came up with the new theory that we all are aware of and using today, that the energy production comes from nuclear fusion inside the cores of the stars, where you fuse hydrogen into helium. The only remaining question at the time was, is there enough of such hydrogen in the stars to be able to do this? And Cecilia Payne showed that actually the vast majority of the component of stars comes from hydrogen, so it's not an issue at all. So this is a bit about how Cepheids were used back in the days. And now, about 400 years after the Mira variables were discovered, it was also realized that the sun also has oscillations, okay? 400 years later. And 10 years after that, it was realized we can use these pulsations to study the interiors of stars. And to try to get a feeling of how this works, I'm going to use an analogy to seismology and earthquakes, okay? So when an earthquake happens, it will send waves that are traveling throughout the Earth, and as these waves hit different regions of different densities, then they will break and reach different parts of the surface than we might otherwise expect. And so by going around and placing seismometers around the surface of the Earth and measuring the arrival times, we can get information about the internal structure of the Earth. And so this was used by Inger Lehmann, who's a Danish seismologist. I'm also Danish, so that's why I'm highlighting this in this instance. We'll use this to demonstrate that the Earth actually has a solid core inside an outer molten mantle. All right? And so likewise, stars also have waves. They're not earthquakes, even though we like to sometimes refer to them as starquakes as an easy way of trying to explain. They happen for different reasons. But because they have these waves, it means we can learn something about the interior properties of the stars. And so the study of waves in planets is referred to as seismology, and study of waves in stars is referred to as asteroseismology. Now, as astroseismologists, we have different goals that we're using, different things we want to achieve by using astroseismology, and one of them is to try to get good measurements of fundamental stellar parameters, such as masses, radii, and ages, but also gain information about and constraints in the interior physics of the stars, such as the mixing profile, their rotation, and magnetic fields. And so the good news across the HR diagram. And so the diagram I'm showing you on the right is my favorite type of HR diagram. It's the astroseismic one, and what it tells me is that if at any point my star passes through any of these shaded regions, then it should start to pulsate. And if it's pulsating, that means we can learn something about the interior properties of the stars from their stellar pulsations. Now, as astroseismologists, something that is really important for us to have is to be able to study and observe the stars for long periods of time to really get good constraints on the pulsations of the stars. So here on the top, I'm showing you the light curve, or what is called a slowly pulsating B-type star that's been observed by Kepler. So each one of these dots you see is a measurement of the brightness over time. On the bottom three panels, I'm showing you what happens to the Fourier transform of that light curve, assuming the star was observed for 30 days, 90 days, and 180 days. And as you see, as the longer we observe the star, on one hand, we're increasing the resolution of this spectrum, meaning that we can measure the frequencies much more precisely than we could before, but also we start to see many more frequencies show up in the Fourier spectrum by observing the stars for this long. And so as it turns out, when we're looking at stars that we really want to get good constraints for, the ones observed by Kepler are really good ones, because Kepler observed the same patch of the sky for 4 years continuously. As it turns out, though, for people like me, who is very interested in studying the massive stars, Kepler was avoiding those stars because they're too bright. So the most massive stars that were observed by Kepler that are pulsating are the slowly pulsating B-type stars, that's situated right here in the center of the diagram. And so these stars are called slowly pulsating because their pulsation periods are about half a day to 5 days total. Yeah? So they're quite long. Now, one of the ways that we try to characterize pulsations, and I'll get back to why this is important in a bit, but it's by using 3 different quantum numbers that are associated with how many nodes an oscillation has. So just like with a guitar string, if you pluck that and you reach certain frequencies, you'll see it has nodes on the string. And similar stars are in 3D, so we have 3 different nodes that these stars can have. There are 2 nodes. The degree L is the total number of nodes on the surface of the star, so these are these wide nodal lines that you see here. And the number M, the azimuthal order, is the number of nodes that are crossing the equator. And the radial order N is the number of concentric nodal shells inside of the star, right? So nodes in 3 direction. You see in the bottom panel some different examples or combinations of number of surface nodes and surface nodes across the equator. Now, if you're looking at gravity mode oscillations, like the ones that are found in slowly pulsating B-type stars, then they have the property that they're roughly equally spaced in period. And what I mean by that is that if you're looking at oscillations that have the same number of surface nodes crossing the equator, and the only difference is the number of nodes that they have inside of them, then if we calculate the period differences between these oscillations, then these differences are roughly the same, assuming that the star is non-rotating and chemically homogeneous. All right? So what we like to do is to take these period differences and plot them as a function of period, and then connect them by a line so we can see whether or not this really is a straight line that we observe for the stars, and these are called period spacing patterns. All right? So by the discovery of period spacing patterns, we can learn what the identification of the oscillations are, which is one of the requirements to do astroseismic modeling. And we can also learn additional information of the stars by studying these patterns. And one of them is related to rotation. So if the stars are rotating, we are lifting one of the degrees of freedom from having the M component to the oscillations. So effectively what is happening is that oscillations that are traveling in the same direction as the rotation will take less time to travel around the star compared to oscillations that travel in the opposite direction. All right? So in this case, where we have oscillations that are traveling in the same direction, it means that the periods of the oscillations get shorter, and you introduce a tilt in these period spacing patterns where the steepness of the slope is determined by how fast the star is rotating. So again, by studying such patterns, we can learn something about the interior rotation properties of the stars. If we look at the effect of the assumption of chemical homogeneous stars, as we know, also in the main sequence, as stars evolve, nuclear burning is happening, and the amount of hydrogen we have in the core decreases over time. So what we're having on the left-hand side is, again, the hydrogen mass fraction profile for about the inner 30% of the star, where we start in blue from around the C8 main sequence, and then evolve the star until the terminate main sequence. And as you see, the core is contracting, meaning we get this kind of a gradient, chemical gradient building up inside the star because of it. What happens to the period spacing patterns is that on one hand, you start to get like a sawtooth-like shape to the pattern, and the overall average value of the period spacing also decreases over time. And that's because the oscillations get trapped by these kind of chemical gradients inside the stars. And the effect of mixing is to change these chemical gradients, and because they're changing, that means the period spacing patterns get affected. And in similar sense, we can then use the period spacing patterns to learn something about the interior mixing properties of the stars as well. So in summary, this is an example of 7 slowly pulsating B-type stars that were observed by Kepler, where each one of these period spacing patterns is for a different star. And again, as I mentioned, the slope of these patterns determines the interior rotation rates of the stars. The average value is related to the mass and the age of the star, whereas the overall morphology of the pattern is related to both the age and the mixing properties of the stars. So by modeling these patterns, these are the properties we can learn about the stars themselves and try to calibrate our models. And so what we try to do for this study is to also increase the number of slowly pulsating B-type stars for which this kind of modeling had been done. So in the past, using data from Kepler space telescopes, there had been four stars that had been modeled. This is again an HR diagram where the shaded region shows you the instability strip, so where these kind of slowly pulsating B-type stars are expected to be found, where the brighter yellow the color, the higher number of pulsations we expected to find for the stars. And so what we managed to do is to increase the sample to 26 stars that we carried out an astroseismic modeling for. That we used different types of information, so we got the period spacing patterns from Kepler. In addition to that, we had a ground-based spectroscopy. They gave us values for the effective temperatures, surface gravity, and metallicity, also rotation, and with, again, distances from Gaia, we also have luminosities that we can use for this type of modeling. We use these parameters in different ways. So the period spacing patterns are what we directly compare to the models, whereas the other parameters we use to limit the parameter space that we considered by the models themselves. The way we carried out the modeling was using a stellar structure and evolution code called MESA. And the way that we define our models is by saying we have a set of varied stellar parameters and a set of fixed input physics. An example of fixed input physics is the shape of these kind of mixing profiles. All right? So whether or not this is an exponentially decreasing function that we have in the convective boundary mixing region, and exactly the shape of this envelope mixing in the envelope as well. And then we vary the size of these regions, those are the free parameters, as well as the masses and the chemical composition of the stars. And we use MESA to do these calculations. On top of that, we put the models into a stellar oscillation code that's called gyre, and use those to calculate what are the theoretical frequencies that we get when we vary these parameters and then compare them to observations. So these are examples of observed period spacing patterns calculated, compared to the best matching theoretical ones that we calculated, where the full lines are the observed patterns and the more shaded or fainter lines are the actual theoretical patterns that were derived. And now I wanted to get into a bit about what we learned about the internal mixing properties of the stars by doing this kind of modeling of the period spacing patterns. So in total, we considered 8 different internal mixing profiles, where we consider 2 different shapes of the convective boundary mixing region, where you just make the core slightly bigger and keep the mixing constant. So that's the bottom panels you see here. And the other one, we assume that the mixing was decreasing exponentially as we go further away from the core. And on top of that, we have different prescriptions for what the envelope mixing might look like. And so what we did, we took these 26 SPB stars, slowly pulsating B-type stars, and tried to figure out which one of these different shapes produced the best match to the observations. And this is essentially the result. So now the number of profiles you see in each one of these subplots is the number of stars that preferred that given type of mixing profile, or that's the mixing profile that did the best at explaining the observations. So you might see here there's no single profile that best explains all of the stars. Unfortunately, that would have been amazing. Yeah, make our life easier. What we do see though is that the mixing levels vary drastically from star to star. But also, if you look at the bottom panels, there are more stars that seem to prefer this step-like function to the mixing profile. But also, if you look here, more stars seem to prefer having this kind of stratified envelope mixing inside the stars. If you look at the parameters, here I'm looking at what happens, how the core mass of the star, convective core mass, correlates with the amount of mixing we have in the envelope. And what I mean by that is we have these green profiles, that is the envelope mixing for the star, and this d-envelope naught value is the amount of mixing at the transition from the convective boundary mixing to the envelope. And so by increasing that value, you're increasing the overall mixing in the envelopes of the stars. The coloration of the data points here on top corresponds to the age of the star that we are measuring in fractions of core hydrogen content, so initial one. So at the 0-8 main sequence, this would have a value of 1, and at the end, at core hydrogen exhaustion, this would have a value of 0. And so essentially we are seeing, as soon as we go above a certain value in the envelope mixing, then there appears to be a correlation between the core masses and the envelope mixing. So the more envelope mixing we have, effectively the higher the convective core masses of these stars get. What we're seeing on the bottom panel is the correlation between envelope mixing and how fast the stars are rotating with respect to their critical rotation rate. Color points here correlate to the initial mass of the star. And what we're seeing here is generally that the faster the star is rotating, the higher the amount of mixing we have in the envelopes of these stars. And that's going to match what we expect from theory. The faster the stars are rotating, the more mixing you get from rotational mixing inside these stars. You may also realize there are a couple of stars, this one up here, that appears to be an outlier. It's a slowly rotating star that has a high amount of mixing. I've added in 2 additional stars that were not studied by us, studied by others, where you also see a lower amount of lower rotation, but moderate amounts of envelope mixing as well. So it's just to say these stars do exist, and maybe it's not the rotational mixing that is the dominant one for these stars. Now what we can do with these models, now that we have them, is try to also predict what the helium core mass would be at the end of the main sequence evolution if we continue to evolve the stars with these parameters. And here you see the helium core mass as a function of the mass of the star, where the coloration of the points corresponds to how much mixing we have in the envelopes of these stars. And what we're seeing generally here, again, the high amount of mixing in the envelope, the larger the helium cores end up being at the end of the main sequence evolution. All right, so that was a bit about the mixing inside the stars, what we learned. The next bit I wanted to talk about is rotation. And what you might remember from earlier, I told you by measuring the slopes of the period spacing patterns, we can gain information about the rotation rates of the stars. That also means we don't actually have to do a full modeling of the stars to estimate what the rotation frequencies of these stars are. So instead of just focusing on our sample, we included also additional stars that are observed by space telescopes, and now plot the rotation frequency as a function of 3 different age indicators for the stars, where on the left we have again the amount of hydrogen in the core with respect to the initial one. In the center is the age as a function of main sequence lifetime, or with respect to main sequence lifetime. And on the right, we're using the surface gravity as an age indicator of the stars. And what you see for these kind of slowly pulsating B-type stars is there's a general decrease in rotation frequency with age. In comparison, we have the gray points over here are the same measurements, but for lower mass Gamma Dorado stars that also have these period spacing patterns oscillating gravity modes, but these are Fa type stars, so they're much lower in mass than the SBB stars. And we don't see necessarily the same kind of relation here, but again, these also haven't been fully modeled to really show these trends. Now, one question we might want to ask here is, on one hand, do we expect to see this kind of decrease in rotation with age? And does in general this match with what we expect from angular momentum transport theory inside the stars? And so what I'm showing you here are predictions for where the star should be in this rotation versus age plots, assuming that we have high, very efficient angular momentum transport inside the stars, so they're effectively rotating as a solid body. So that's in blue. And the hatched orange region, what we're seeing here, is what happens if we have no angular momentum transport in stars. And I wanted to highlight what turns out in either case, the star's rotation does decrease over time, but by how much is really dependent on how efficient the angular momentum transport is. And what I really want to highlight here is that we have an area in these diagrams where we don't see any stars, and this is indicating that angular momentum transport appears to be very efficient inside these stars, and is definitely taking place for these type of SVB stars on the main sequence. Now for the remainder of the talk, I wanted to talk a bit more about the more massive stars than the SVB stars. So those were the most massive stars we could observe with Kepler. As it so happens, now we have other telescopes we can use to study these stars. And a telescope that I'm really excited about is the TESS telescope. So the Transiting Exoplanet Survey satellite, that's main mission is to observe exoplanets and study planets, just like Kepler, but way more studies is happening for stars with these type of telescopes. Yeah? The good thing about TESS is that it's not confined to one patch of the sky, but it's essentially doing a full sky survey and returning to fields that it has observed before, and is observing for a minimum of 27 days, but there are parts of the regions of the sky where these observing sectors overlap, where we get longer light curves as well for these stars. And so we looked at some of the first data from TESS just to show, if you're looking at the massive stars, this is a color magnitude diagram from Gaia data, Gaia DR2 at the time, and just look at all the different types of variables that we find. So all the different symbols here just corresponds to a different type of variables. What we're seeing here is that for the high mass stars, we have a lot of different types of variables that we can be studying with TESS, and it's really exciting that we get these opportunities now also from space to observe these stars photometrically. What I'm in particular excited about is the opportunity to study OB associations. So those are groups of stars that are similar to open clusters and globular clusters in the sense that they were all formed from the same molecular cloud, and so should have roughly similar ages and chemical composition. The differences between these three groups of stars is the number of stars that we have in them, how old they are, and whether or not they're really gravitationally bound as well. And so for the OB stars, OB associations, those are called as such because they have a high number of OB stars in them. And so these are really the main focus of my study right now. The ones that I'm focusing on currently are a group of associations that are found in the constellation of Cygnus, right here, the Cygnus region, where recently the membership of these OB associations was redetermined using data from a Gaia Space Telescope. And in total, these associations have about 650 O-type stars in them. So we're going through and studying these stars with TESS. They were all observed by TESS. And these are just some quick numbers just to demonstrate the number of pulsating stars that we have. So there are more than 300 pulsating stars that we find. Here's an example of a light curve from TESS and the Fourier transform of said light curve. So this is again a slowly pulsating B-type star in this case, observed by TESS. In addition, we also find a different type of variable that has also only relatively recently been discovered using data from space telescopes. And these are the stochastic low-frequency variables, where what you're seeing is in the power density spectrum of the light curves of these stars, there's an increase in power of the spectrum as we go towards lower frequencies. So it's kind of a red noise signal that we're seeing for these stars. And out of all the stars we considered, where this was the dominant signal, we have about 49 of such stars. Now, the way to characterize these signals you can do in different ways, and I wanted to discuss two such methods. This is again an example of such an SLF, so a stochastic low frequency variable, where you have on the top is an example light curve for such a star. On the bottom left panel, you see the power density spectrum, and on the right, you see a cumulative integrated power spectrum that is normalized to 1 at a given frequency, where essentially we're measuring what the power is, integrating power of this power density spectrum over frequency to measure at what power, at what frequency do we get 50% of the power, for example. So standardly, this type of variability is similar to the red noise caused by granulations as seen in solar-like stars. And in these cases, people use Lorentzian functions, models, to try to describe the shapes of these kind of profiles of the stars, where you get a set of three parameters that is related to the amplitude, the slope, as well as the knee breakpoint, where you have this turnover, this characteristic frequency of the star. So that's one of the methods that we use to characterize the signal. The other one calculates the root mean square of the variability of the light curve, and then determines the frequency at 50% power, and then what we call the width, which is the frequency at 80% minus frequency at 20% divided by the 50% frequency, to give a measurement of the width of these spectra. The reason why we're doing this is because if you're fitting a model to the data, your result is going to depend on what type of model that you're using, and there are different models that are being proposed, where in this case you get around the issue of selecting a model essentially to fit the spectrum. And so what we're finding, if we're plotting these parameters as a function of the luminosities of the stars, we're seeing these general trends. So the blue are the data we're finding for the OB associations that we studied. Orange are data that have been stars that have been studied previously by Dominic Bowman. And on top of that, we include as a pink star also a star in the Small Magellanic Cloud, where we also find this type of signal for the stars, just to show that at similar luminosities, this kind of variability seems to be pretty much the same, independent on the metallicity of the systems. Why am I mentioning this? Well, that's because the origin of these signals, where they're coming from, is still something that is under debate and being discussed at this time. And I'm trying to illustrate, mentioning a bit about the different mechanisms that can lead to this type of variability by using this type of diagram, where we're just looking at the characteristic frequencies and then our groups of measurements here. So that these lines you see here are the estimates from granulations in solar-like oscillators that have been studied previously. The other type of theory behind this type of variability is subsurface convection zones. So when you go up in mass, you have a region inside the star, so towards the surface, an increase in the opacity caused by iron group elements. And because of this increase in opacity, you also get what we call a subsurface convection zone that is located below the surface of the star, but is not big in the sense as what you see with the outer envelopes of red giants and solar-like stars. So those are essentially internal gravity waves excited by surface convection. We have also internal gravity waves excited by core convection. So essentially, when you have convective cells that are bumping against a radiatively stable region, those will give rise to waves that propagate throughout the star. And so another theory behind these signals is that they're caused by the cores of these stars. So what you're seeing here, the different points, these ones right here are results from simulations of subsurface convection or outer envelopes of, we have a 35 solar mass star and a 30 solar mass star, where this is near the main sequence and what happens to the signal as you're evolving the star. So this is around mid-main sequence that we're seeing. For the internal gravity waves, we have also measurements over here from simulations of this type of signal, whereas others have repeated these kinds of studies for different masses as well, using some different assumptions for the models, and find much lower characteristic frequencies than some of the other results. Another theory behind the origin of these signals is also stellar winds. Radiatively driven stellar winds for very massive stars can also give rise to these kind of signals themselves. And again, it's still a bit under debate where they're originating from. Now, for the final bit, I wanted to very briefly talk about fast yellow pulsating supergiants and the puzzle that we have been involved in trying to solve for these stars. So I wanted to say again, TESS is amazing. TESS does have some complication, things you need to keep in mind when studying stars observed with TESS. And that's a factor that comes into place for these types of fast yellow pulsating supergiants. So these types of stars are again yellow supergiants located around here in the HI diagram and are quite massive, so more than 15 solar masses and above. And what has been found for these stars is that they seem to have oscillation frequencies in their power spectra when we're looking at those. These stars were all found in the LMC and SMC, so large and small Magellanic Clouds, and were first discovered by TESS in 2019. And now they're called fast because of how what their frequencies are compared to the acoustic cutoff frequency for these stars. So what does that mean? So if you're looking at the frequency limit, how fast a star can be pulsating before the pulsations escape the surface of the star, that's characterized by something we call the acoustic cutoff frequency that depends on the sound speed profile inside the star, as well as the density scale height for the stars. And so essentially, if your oscillation frequencies are less than this acoustic cutoff frequency, then the oscillations get reflected at the surface and are trapped inside the star, and we can observe them because of the changes to the radii and temperatures of the stars. If the frequencies are higher than this, then they escape the surface and dissipate, and we would not be able to observe them. So essentially, this acoustic cutoff frequency puts an upper limit to the frequency of oscillations that these kind of stars should have, and gravity mode oscillations are lower than these acoustic frequencies for comparison. So if you're looking at here on the right, we have an HI diagram showing different lines here. So there's a sample for the LMC and SMC for these fast yellow pulsating supergiants. The lines are evolutionary tracks for different initial stellar masses, where we go from about 15 to 35 solar masses. And on the right, you see the lines again and what happens to the acoustic cutoff frequency as the stars are evolving. So it's decreasing over time. More specifically, you'll see that most of the stars where these kind of signals have been found in have frequencies that are higher than these acoustic cutoff frequencies, and also they're moving towards the upper right, whereas with mass, you go closer to the lower left in these type of diagrams. So there's a potential issue here. Is there something wrong with the theory behind the oscillations, or could there be something else happening for these stars? And what we have to keep in mind when studying stars observed with TESS is that the pixel size of the TESS CCD are very large compared to other telescopes such as Kepler. So I'm trying to illustrate that here. Where you see on the left is an image of an open cluster, M67, where you have here a K2 superstamp of this cluster, and the same image of this cluster observed by TESS, where we have these lines are just to guide the orientation of the image. And as you'll see here, the TESS pixel sizes are about 5 times larger than Kepler, so the resolution you get is much lower, and you have an increased risk of contamination for these stars. So there's a risk that you have a star nearby that is showing signals from a variety of sources that might bleed into the pixels that we're interested in observing for these stars, or you have multiple stars in the same pixel as well. Now, a way to try and circumvent this and figure out where does the source of my signal come from is to use tools such as a TESS localize, where what they're really trying to utilize here is that even though the spatial resolution is large, the time resolution that we get is high instead. So essentially how this code works is that it just takes as input a set of frequencies that we find in the Fourier spectrum of the star. So here on the left, you see an image taken by TESS, where you see the coloring determines how much flux we get for the star. So this is a target pixel file. The star of interest is this red one in the center, where this hatched region is the pixel mask that was used by the TESS team to extract a light curve for that star. And on the right, you see the Fourier transform of said light curve, where we observe two different frequency groups, one at the lower frequency end and another at a higher frequency end. So in this particular example, if we take this lower frequency group and put those frequency into the code, we essentially go through each pixel and determine what is the amplitude or signal to noise we get for frequencies, for these frequencies, for the amplitudes of these frequencies in each pixel. In this case, we have higher signal to noise right here. You then apply a pixel response function that tells you something about how we expect the flux to fall for a star, model that, and then end up determining what's the position of the source of the variability. And so in this particular case, this example, you have a star down here that is contaminating the signal of the intended target star. I could tell you for the second group, I don't have the figures here to show, but for the pink group, the higher frequency group, those two come from the target star intended. Okay? So this is just to say we have to be a bit careful when studying stars observed with TESS. In this case, I'm just going through one of the FIPS prototype, fast yellow pulsating supergiant prototype that we have, where you see, again in red, the star position is the source that we're interested in. Now on the top right, you see first the extracted light curve for the star, assuming the pixel mask picked out by the TESS team and the corresponding Fourier transform, where we have 3 signals right here, indicated by dashed lines. If you decrease this mask size and just look at the light curve and Fourier transform, you'll see that these signals go away. And instead, as it turns out, if we go and have a look at nearby stars and extract the light curves, what we realize is that each one of these signals are coming from 3 different nearby stars that are contaminating the light curve of this otherwise newly identified type of variable star. Now, it becomes maybe a bit easier to see if we do a phase folding of the light curves using these frequencies. And what you see here is actually happening. I'm stuck, so I'll do this. So we use each one of the 3 signals to phase fold the 5 different light curves. And as it turns out, each one of these signals, each one of these stars, come from a nearby binary, 2 of which were already known to be binaries. And one of it's here in the center, this one right over here, is a new binary. But all 3 are contaminating the signals for these stars. And as it turns out, using this kind of code to try to study the source of the variability, we can't concretely say that any of the signals that have been found for these types of variables are actually coming from the yellow supergiants. And so with that, I'm going to leave you with my conclusions, and I hope I convinced you that asteroseismology is really an amazing tool for studying stars. We learned a lot about the interior mixing and rotation properties of slowly pulsating B-type stars. They're a bit more complicated than we had hoped, perhaps, but nevertheless very interesting. And now with TESS, we really have a lot of opportunities to study the most massive stars that we have, but also there are some things with contamination we have to be a bit careful of when studying these stars. And so with that, I'm happy to take any questions you might have.
The 26 SB.
Yes.
How many are known binaries?
How many of those are known binaries? Oh, so there are 2 of them, from what I remember, that are known binaries. For the others, we don't necessarily have enough spectra to tell if they're spectroscopic binaries, but at least it's not showing up as eclipsing binaries in the light curves. Yeah.
So on binaries, do you you looked at the effect of mixing and how it impacts the oscillations, but have you considered like mass loss and mass gaining models? And
not for these so far. So again, things get more complicated when we study binaries. Yeah? Right now, one of my next projects, for example, is to look at if we have binary interaction products, how well can we use stellar pulsations to actually determine whether that star was in a binary system previously, or whether it's coming from a single star, to try and see those differences. So that's not something that has been done that much before. There's a recent paper out studying really binary mergers for much more massive stars as well, to see can we distinguish between these scenarios. So it's true if you have a binary system, for example, so one of the SPB stars that were rotating is actually in a triple system, and they found by really doing really sophisticated techniques for these stars that the inner about 96% of the star is rotating rigidly, but the outer bit is rotating fast, really fast in comparison. And I think that's because of the interactions from the nearby with the inner two components of the system that is impacting it. And it's also known that binary interaction can also induce internal gravity waves in stars and lead to mixing. It's not something I've looked at, and I think a lot of people, at least in the context of asteroseismology, has looked at, but something I find really interesting. So if you have suggestions, I'm happy to hear where it might be best to start for these types of stars.
Any more questions? Yes.
Great, thanks for the talk. Just start off. I think you had that plot of the mixing efficiency versus the rotation, and you mentioned that there were those two, the red points, those stars that had high mixing efficiency but really low rotation. So what's different about those? Do you have any clues into what's happening?
So one of the other mechanisms for mixing, and what has been shown, is again internal gravity waves excited by core convection are also efficient at mixing material inside stars. So I think in that instance it might be that this is the dominant mechanism for these stars. Otherwise, specifically, again, we did some simplifications when doing this ensemble study that we had. And what we really like to do is to dive into some of these stars in more detail to figure out in what ways are they different. At this point, I don't have a definite answer for you. I'm just saying I think it's probably another different mechanism that is, mixing mechanism that is dominating in this case.
Technical question on one of the plots. So
Sure.
on the rotation versus age or essential hydrogen slide, how do you measure the essential hydrogen or age? Was it from your photometry, or is it?
So for those with how much central hydrogen is left, that's from asteroseismic modeling. So that we have to do the full asteroseismic modeling. For the stars in the central plot, so it's all the same sample, but for some stars there is only a measurement of how old the star was with respect to main sequence age, and those estimates are based on comparing the position of the star in the age diagram to evolutionary tracks. So it's quite an uncertain age measurement, but that's all we have for some of the stars. So it would be something I'm interested in, is diving into some of those stars again now with TESS, since we have this data to try to study them.
When you said the hydrogen fraction is from modeling, is there a degeneracy between the rotation and the essential hydrogen fraction?
So that's what I was showing, that the rotation appears to be decreasing as the stars become older, so you have less hydrogen in the core. And that again has to do with as the stars evolve on the main sequence, they also become brighter and bigger. So it's more of a relation with the radius of the star that's playing in here and the effect on their rotation.